Hi guys, in this video, I'm going to cover conditional probability and Bayes theorem. So the conditional probability first. Let me start with the equation. Probability A given B is probability A intersection B over probability B. So the conditional probability means that here you condition on the event B and you calculate the probability A given this situation. So in terms of the equation, you have a probability A intersection B over probability B. Then if you want to calculate the probability B given A, that is probability B intersection A over probability A. As you can see, the numerator, they are actually the same. Doesn't matter, you have the probability A intersection B or the probability B intersection A, they are the same. The order doesn't matter. So you are taking statistics course, but at the same time, you are taking the finance course. So you take the finance course or you're taking statistics, they are the same. But then the denominators are totally different. That means that even though they have the same numerators, these two are totally different, okay? So let's start with the example. Here, with this contingency table or the 2A table, we first want to calculate the probability A given B here. So let me use this equation. Probability A given B is probability A intersection B over probability B. So in order to calculate this one, you need to find the marginal distribution. So the B, the total number is, doesn't matter A or the A complements. So that means that here is a 60. So I just find the summation of these two. And then same as for the B complements, that's a 70. And then the A complement is a 70, A is a 60. So the total is a 130. Then you can find the probability B, the denominator first. So the B is 60 over 130. So the probability is a 60 over 130. What about the probability A intersection B? So A intersection B is a 40 out of the 130. So that means that 40 over 130. So we have a complex fraction. These 130s are canceled out. We have 40 over 60. That is same as 4 over 6 or the 2 over 3. There is another way to find this probability A given B with this 2A table using the intuition. So the condition on B means that you narrow down the set to the B. So the B, given this B, you want to find the probability A intersection B means that 40 over 60. So you got the same answer. Then for the question B and C, you can use the intuition and find the answer right away. So the probability A given B complements. So that means that here, given that B complements, you find the A. So that is a 20 over 70. And then the probability A complement given B complement. So given B complement, you want to find the A complement. So that is a 50 over 70. And then the last question asks you whether these two events A and B are independent or not. So there are two ways to check that independence. The first one is broader meaning of the independence. So probability A given B equals probability A. Then we say that these two events are independent. So whether you condition on the event B or not, the probability is the same. Then automatically, this one holds as well. Probability B given A equals probability B. So these two are the broader meaning of the independence. And that means that there is a narrow meaning of the independence, that is probability A intersection B equals probability A times the probability B. So in fact, this narrow meaning of the independence comes from the broader meaning of the independence. Here's why. Well, you can write down the probability A given B equals probability A. Then the left-hand side, like I introduced the equation, this is a probability A intersection B over probability B. So then the cross multiplication gives you probability A intersection B equals probability A times the probability B. So that's why we call it, this one is a narrow meaning of independence because it comes from this first one, broader meaning of independence. So given that, can we check that whether these two events are independent or not? And which one do we need to use? It doesn't matter, but in this case, we already calculate this probability A given B. So probability A given B, we found that that is a 2 over 3. What about the probability A? So probability A is here. 1 second. So probability A is a 60 over 130. 60 over 130. So they are not the same. That means that they are dependent. So even though we didn't check that probability B given A equals probability B, or the probability A intersection B equals probability A times the probability B, so these are not equal, because if the first equation does not hold, then these two, the other two, does not hold, they don't hold as well. Okay. Now here, the following question: suppose that E and F are two events, and probability E and F is a 0.1. So in probability, when you have this and, that's the intersection, and or is a union. So let me denote the question here. Probability E and F is a 0.1, and probability E is a 0.2. And then the question asks you find the probability F given E. Then probability F intersection E over probability E. Numerator is a 0.1 because, like I said, probability E intersection F or the probability F intersection E, they're the same. And denominator is just 0.2. So the answer is a 1/2. And then the question here, probability A is a 0.9, probability B is a 0.3, and we have the information. It says that A and B are independent. Given that, can you find the probability A and B? Yes. We can use a narrow meaning of the independence. Probability A and B equals probability A times the probability B. So the right-hand side, we know that probability A is a 0.9, probability B is a 0.3. You just need to find the multiplication, then you can find the answer. That is a conditional probability and some examples. Now let's go to the Bayes theorem. So first, here is the situation that you face to solve these questions. Well, you know the probability A given B, which is given as 0.7, but in the end, you want to find the probability B given A. That's a Bayes theorem. You know the A given B, but now you want to find the B given A. So by solving this question without any context, you will get to know how to use the equation properly. But in the following example, I will give the intuition and why we need to study the Bayes theorem and how powerful it is. So first, let me write down the equation because we want to find the probability B given A, right? That is probability B intersection A over probability A. Then you go back to the question. Do we know the probability B intersection A? No. Do we know the probability A? No, it's not given, but we need to figure it out. So first of all, we can find the probability B intersection A by using these two. How? Well, probability A given B, which is a 0.7, that is same as a probability A intersection B over probability B. Then here, probability A intersection B over probability B is a 0.7. So how about the left-hand side? This is a thing that we want to know. And probability B is given as 0.55. That means we have a one equation, one unknown. Probability A intersection B over 0.55 is a 0.7. That means that probability A intersection B equals 0.7 times 0.55. So we found the numerator, which is 0.7 times 0.55. How about the denominator? Well, here, I can visualize a situation with a Venn diagram. So the left box is a B, and the other box, the right box, is a B complement. And inside of this B, we can have this A. Okay. Then, as you can see, so this is A. Here, this part is a intersection B. And the other side here, that is A intersection B complements. When you put it together, that gives you the A. That means here we want to find the probability A, that is probability A intersection B plus probability A intersection B complements. So what's the point? If you go back to the question here, we already found that probability A intersection B, that is a 0.7 times 0.55. This one, same. And then we just need to find probability A intersection B complements. So these things that we didn't use it yet. So by using this one, you can find it. Same as probability A intersection B here. Probability A intersection B complement is same as probability A given B complements times the probability B complements. That is 0.8 times 0.45. Okay. Then you can find that the answer, probability B given A. Here, let's go back to the Venn diagram. And you see that this event B and the B complements, they are disjoint. They are mutually exclusive. And they are collectively exhaustive. In that situation, we can find the probability A by using these two. A intersection B plus A intersection B complement is A. And then it requires a few steps, but you can see that how we use this equation to come up with the probability B intersection A, like here. And how can we find the probability A? Well, using this Venn diagram, you can visualize the situation. It turns out we can find these two. Then after that, you get to know the probability A. So that's how you use the equation and find the answer for this Bayes' theorem question. Now let's take a look at this example. So the probability that a person has a certain disease is known as a 0.05. So let me denote the question. So probability D is a 0.05. So D means a disease. And then he or she take the test and it tells us as a positive or negative, right? Take a look at this part. If the disease is actually present, the probability that the medical diagnostic test will give a positive result is a 0.88. That means probability, given that someone has a disease and the test is a positive, that is 0.88. What do you mean? Well, even though if someone actually has a disease and he takes a test, it says that positive is 88%. That means the test is not perfect. That means that here, even though someone has a disease, it is possible to say that the test is negative. That is 0.12. We can also make a diagram like this. So someone has a disease or someone does not have a disease, the complement. This is a 0.05. That means that 0.95, 95% probability he or she does not have any disease. And then they take the test and test says a positive is a 0.88. This one is a 0.12. So same as here, this one is following. If the disease is not actually present, the probability of a positive test result is a 0.04. That means that here, probability, someone does not have a disease, but then the test is a positive, that is a 0.04, 4%. So here, this is a 4%, then with the probability 96%, when someone does not have a disease, but then the test says a negative, that is a 96%. So you can also write down the equation as following. Now, question A, if the medical test has given as a positive result, what is the probability that the disease is actually present? That means that we want to find the probability given that someone get the result, which is positive, and he or she actually has a disease. Okay, so as you can see, you know that probability positive given D, but now you want to find the probability D given positive. So that is a Bayes theorem. Then same as a previous question, you first write down the equation. That is a probability D intersection positive over probability positive. So the numerator is a probability positive given D times a probability D, okay? And denominator is a probability D intersection positive plus probability D complement intersection positive, okay? So the numerator first, 0.88 times a 0.05. And denominator, this one is same. And probability D complement intersection D is using these two here. So probability positive given D complements times the probability D complement. That is, this one is a 0.04 and this one is 0.95. So let me skip the calculation. That is a Bayes theorem. So let me cover another question here. A banking executive studying the load of the trust in crossing customer advocates has determined that 44% of the banking customers have complete trust, 45% moderate trust, 11% minimal or no trust. So here, you can make a tree diagram like this. So 3 different customers. The first one is a complete trust customer, 44%. Moderate trust is a 45%. No trust, minimal trust is a 11%. And then of these banking customers that have a complete trust, 69% they are very likely to recommend their primary financial institution. So let's say that he or she is using the Chase Bank and he or she is a complete trust customer, then he or she wants to recommend their primary financial institution to their friends, neighborhood. That is a 69%. So here, recommendation or no recommendation. So that is a 69%, then automatically the probability they don't recommend is a 31%. Moderate trust, on the other hand, 17%. So here you see that 70% of this moderate trust recommend their institution. So 0.17 R and R complements. So this is automatically the 83 because it's complement. And then 1% of the minimal trust or the no trust, they recommend their institution. So here, of course, you can denote these numbers. So for example, this 0.69 means that probably, given that someone is a complete trust customer, he or she recommends the institution is a 0.69. Okay. How about this one? Well, probability, given that someone is a moderate trust customer, he or she does not recommend this institution is 83%. Okay. Now the question A, compute the probability that if a customer indicates he or she is very likely to recommend his or her primary financial institution, the banking customer also has a complete trust. So we want to find, given that someone recommend his or her primary financial institution, what's the probability it turns out he or she is a complete trust customer? Okay. Well, that's a useful information because let's say that someone recommend Chase Bank to you. Then you want to know whether this guy is a trustful or not. So then we want to calculate this one. Same as before, you first write down the equation. So complete trust given R, recommendation is a probability CT intersection R over probability R. Then this time, let me check the denominator first. So there are 3 different the recommendation. The one is by the complete trust, and the second one is by the moderate trust customer, and then the last one is a no trust or the minimal trust customer. So that is a probability, recommendation, and complete trust. Probability, recommendation, and moderate trust. Probability, the last one is recommendation and no trust, minimal trust guy. So this one is the answer, right? And same as before, this one is a 0.6 times a 0.44. So 0.6 is a probability R given CT times a probability this complete trust customer is a 0.44. Okay. Then the second one and third one is same. This one is a 0.6 times a 0.44. The second one is a 0.17 here times a 0.45. And then the last one is a 0.01 times a 0.11. Okay, so that's how you use a Bayes theorem. And this 2 example gives you the intuition why we need to understand this conditional probability to find the answer. So for example, you can have the different types of the example like this. So let's say you met someone and then he or she said that they have an internship experience, but you want to know whether he or she is a first year student, sophomore, junior, or senior. So there are four different students: first year, second year, third year, and fourth year. And then let's say that the proportion, first year students is a 40%, second year students is a 30%, third year students is a 20%, and the fourth year is a 1%. I just come up with the numbers. And then they either have an internship experience, yes or no, okay, like this. So first year students, only the 10% of students, they have an internship experience, 90% then they don't have. Second year students, let's say that 40%, they have an internship experience, 60% they don't have. Third year students, so 70%, they have an internship experience, 30% they don't have. The fourth year, the senior students, 90% of the students, they have an internship experience, 10% students of the fourth year, the senior students, they don't have the internship experience. So then you can find that this one, given that someone said that I do have an internship experience and you want to find out what the probability is a 30-year student, okay? So using the Bayes theorem, you can find it. So let me leave it to you.